All right, so I'm going to go through the exam answers. I'm going to talk about the exam in general. You know, there were quite a few perfect papers. Actually, a lot of perfect papers. So obviously, those people got it, right? They got it. They can get a perfect paper, a lot of perfect papers. But then there's a lot of people who did poorly. And if you did poorly, it means you're missing something. You didn't get it. It doesn't mean you can't get it. It just means you didn't get it yet. Right? So if you got a low score, you need to start thinking about what happened. You know, maybe I didn't study the right way, or maybe this discipline is not the right discipline for me, if it happens to fall in your major. But I think most of you, if not all of you, are capable to do well on the exam. And the issue is your approach to learning the material. And I try to explain how to approach it, but it's going to take effort from you. And maybe my explanations is insufficient. Okay, that's a possibility. But I'm doing my best. So I don't think I can do better. I know I can do better. So I'm always trying to do better. But so that's one thing, is my explanations, and of course the book as a resource, and the internet as a resource, and the TA, and the computer science club, and the computer science club tutors, and the help desk. You got a lot of readers surrounded by a lot of resources that you can use to figure out how to do well in this course. It's not just about doing well in this course, it's about understanding computer programming, understanding how computers work, how to program a computer. And that's obviously a very relevant skill and understanding to have in today's world. So I don't have to talk much about that. So it's probably, in my guess, is it probably has to do with your study technique. I would guess most people are not spending enough time on it. You got too many distractions. There's lots of interesting things that are probably more interesting to you than studying for, this material. And cramming the night before the exam, that will never work. You've got to be training. It's like you're in training. You're going to run a marathon. You can't do training a day before the marathon. You've got to be training from day one, every day. You've got to put in those hours of study. And when you study, you can't just read. You can't just watch the lecture videos that I record. You have to challenge yourself. You have to push your own mind to, you're in charge of your learning. You have to create problems on your own, not just take the problems I give you. Invent problems for yourself. Say, well, I don't fully understand the difference between n++ and ++n. I don't understand the difference between post-increment and pre-increment. And I've looked at the instructor's problems. I've listened to his video on it that he recorded when he lectured about it, and I still don't fully get it. So what do you do next? Well, you can start creating problems. You say, well, let me throw out a problem. What would happen if I print n++ times 2, right? And then you think it out. You create your own mental challenge. And then you practice. You say, well, if this was, an exam setting, for instance, what would I come up with an answer? And then after you come up with your answer, then what do? You want to verify it. So you write a small program and you code it up and you see whether what you figured out is what the program is actually producing. I'm just giving you an example of what I think you need to do to study in this class for this work. This is a lot about creative problem solving. It's about reading code, obviously, understanding code, and then it's also about creative problem solving. When you're faced with a problem, how do you come up with the solution? And I demonstrate a lot what I believe to be a good technique, which is iterative development. You break the problem into pieces. You don't do the whole thing all at once. You chisel away at it. Of course, in the exam, the problems are very small. So there's not a lot to do there. The exam is mainly focused on very small programming problems. And whereas the lab exercises are focused on slightly bigger, well, obviously larger programming problems. And by the way, for the labs, don't just get a copy of the lab solutions and write it down and submit that. That's not going to help you. Unless you don't care about learning programming, unless you don't care about, you're doing a different major and you're saying, well, I'm not interested, I don't want to spend the energy on this. But if you're in a computing major in particular, you're going to need to develop the skill to solve those problems, those lab exercises. You need to develop the skill to solve those problems on your own, not just copying a solution that I present or that the TA presents or that you see, that your friend shows you or you find on the internet or whatever. You need to practice working out those solutions on your own. And you're building a new set of mental muscles, a new set of mental tools that you're going to use to apply and solve those kind of computing problems. And once again, these problems are so important in today's society. I mean, they are everywhere. They're even in factories now. When I was young, I went into a factory. My father was involved in running a factory. I used to work there. I used to go in and work on these presses, metal presses, punching holes in metal, and everything was very manual. And now you go into a factory and you program equipment. Even in that situation, you have to know programming. So it's just creeping in pretty much everywhere. This reality of automation, information automation, and of course automation that controls not just information, but controls physical devices as well. So obviously it's important. So I don't need to talk about that too much. Let's get on to the exam now. Let's look at the problems, and I'll explain the solution to the problems. Okay, let's look at number 1. When the code in figure 1 runs, what does it output to the console? All right, let's look at that one. So we've got, I'm scanning through there. There's only one variable I. We initialize it to 1 to begin with. Now, how many top-level statements are there in this snippet of code? How many top-level statements are there? Anyone can see that? What do I say when I say top-level statements? There's 2. There's a definition of a variable I and its initialization, and there's a while loop statement. There are 2 top-level statements. There's some substatements, and the while loop has 2 substatements. There they are. These are substatements. They're statements within an outer statement. And the statements are run one after another. We first do the first statement, then we do the second statement. The second statement is complicated. It's a complex statement in the sense that there's repetition of substatements inside of it. But you should look at this as 2 statements at the top level. And the first statement creates an I, initializes it to 1. And now the second statement is this loop. It's a while loop. So that means we've checked the loop condition, execute the substatements. After checking the loop condition, we execute the substatements when the loop condition is true. When the loop condition is false, we have finished executing the while statement. It's done. So I equals 1. I is currently 1. That's our record of it here. And that's less than 32, so we're going to do the substatements. So C out I minus 1. Well, I minus 1 is 0. So we're printing 0. We print a 0. We print it there. And then we print a space. And then we're done this first substatement. Now we do the second substatement. But notice that first substatement didn't modify I. It just used I. Now we're going to modify I. We're going to set I equal to 2 times itself. So I is 1, so 2 times 1 is 2. We write 2 into I. We copy the value 2 into the memory location labeled by I. I becomes 2. I'm going to make, in addition to a mental note, I'm going to make a note in my editor that I is now 2. Now that I finished the substatements, now I'm going to check the loop condition. I less than 32, that's still true. So we're going to print again. I is 2, 2 minus 1 is 1. So we're going to print 1, and then a space. And then we double we double I, which is 2. So now this expression is 4. 4 is assigned into I. So now I becomes 4. Check the loop condition, it's still less than 32. So we print I minus 1, which is 4 minus 1, which is 3. And a space. And then we double I again. When I is 4, when we double I, it becomes 8. Now we compute 8 minus 1 is 7. We print 7 and a space. And then we double I. Don't get lost. We're not doubling 7. We just printed 7. I is 8. We double 8. Now it becomes 16. And then we print, and the loop condition is still true. 16 is less than 32. We execute the first substatement. We compute I minus 1, that is 15. And we print a space. And then we double I. Now I becomes 32. Now we check the loop condition. The loop condition is now false. So we do not run the substatements. And we're done the while statement. We're done. And that's the last statement. There's only 2 statements at the top level. So this is what the program prints. All right, let's look at the next one. When the code in figure 2 runs, what does it output to the console? Let's look at this. We have two variables to keep track of, n and k. There's an n, and there's a k. And I'm just going to keep a note there so I don't forget them. All right, the first line, we initialize n to 1. In the second line, we create the k, and we assign a value to it. Okay, what value do we assign to k? Well, we need to evaluate the right-hand side of the assignment operator. So it's n++, it's a post increment, means we do it later. So we take the n, which is 1, multiply by 2, we get 2. We assign 2 into k. Oh, and now we got to do the post increment. Now, n gets bumped up to 2. And that's the order. Now we go to the next line. And we've got an output operator, so we're going to print something. So we need to evaluate the right-hand side of that output operation. This is a pre-increment with n. That means we do it first before we use the value in n. Right, that's different. We do the increment early before we use n. Back here, we used the value n, and then we incremented after we copied and read and used the value n. So let's go ahead and increment n. N becomes 3. Multiply by 7, that's 21. And 21 plus k is 23. And we print that. So any questions on that? What about number 3? Suppose that t is an integer variable. So t is an integer variable. We don't need, when I say it like that, we don't need to declare it. If you do declare it, that's okay. Suppose that t is an integer variable. Write code that prints cold when t is less than or equal to 40, cool when t is greater than 40 and less than or equal to 60, warm when t is greater than 60 and less than or equal to 80, and hot when t is greater than 80. So this problem, a lot of people had trouble with this problem. So I think next quarter I'm going to spend more time preparing students for this type of problem. Okay? I don't think I gave you enough problems to work on this. All right, let's take a look. There's actually many possible solutions. Let me show you the most common solution that I saw in the exams. All right, here we go. So if t is, less than 40? Less than or equal to 40. Then print cold. Else if t is greater than 40 and, which looks like that, t is less than or equal to 60, then print cool. Else if t is greater than 60 and t is less than or equal to 80, then print, I'm going to guess, I think I did warm, right? Is that what I did? Else if t is greater than 80, yeah, it's warm. If t is greater than 80, then print hot. I would say that's the most common correct answer that I saw. All right. Now I'm going to show you some variations. All right, let's look at variation 1, which looks just like this. See, if t is less than 40, we're going to print cold, and that's the end. We don't go to the next test. If t happens to be 30, we're not going to even run this test anymore. We won't run that because it's an else clause. If something, then do it. Else do, well, if I'm already the something, I'll just do that. I don't have to do the else part. You see that? So that means we know if we get to this test, it means that t is bigger than 40. It was because if t is not less than or equal to 40, we know that t is bigger than 40, and therefore this is redundant. We just have to check to see. We already know that t is greater than 40. We just have to check to see if t is less than 60. And if it is, we print cool, and that's the end. But if t is not less than 60, what does it mean? It means t is bigger than 60. Well, then this becomes redundant. We don't have to test that. we just check to see that t is less than 80, less than or equal to 80. And if t is less than or equal to 80, we print warm and we're done. But if t is not less than or equal to 80, it means we're bigger than 80. Well, then we don't even need no business. We just have an else clause there, because that's the only other possibility is t is greater than 80. Do you see the simplification? This is how I would have solved the problem. That would have been my answer. But they're both okay, because this, if this is more readable for the people who are reading the code, then I would say that's a better answer, even though it's wasteful, because it does more calculations than it needs to do. Of course, if you were in a process that was executing very often, then that would be wasteful. But normally, with this kind of code, it's not in a time critical loop, and it's not running frequently. And so some waste in order to provide better readability is okay, is good. It's a good thing, because a bug is worse than a bug is worse than some unnoticed time waste. If this thing runs once a minute, so what? I mean, if it runs every millisecond, then maybe you want to tighten it up a little bit, but that's not common. Actually, it is common. It is common. So keep that in mind. Let's look at even another solution. Maybe this one is even more readable. Maybe you're not comfortable with else if. Then you could have answered it like this. That would be good. Now we test the first if it's true, then we print cold. And whether we print cold or not, we're going to execute the next test. So we need to keep this in. If t is greater than 40 and less than or equal to 60, then we're going to print cool. So we have to we can't take it out like over here. Here we use the else clause, see? So we could remove that part of the test that we already checked. But here, we're not using an else. We're actually always evaluating 4 of these if conditions, always in the code. We're not skipping any using that else keyword, that else construct. We're always running these tests. And these are mutually exclusive. These tests are mutually exclusive. In other words, only one of these tests can be true. If one is true, then the other 3 are false. So you could write it like that. That's another solution. Any questions? Okay. What about figure 3 here? When 3 runs, what does it output to the console? So problem 4. So we have a k, an n, and an I. There's 3 variables. When k is created, it's initialized to 23. N is created, it's initialized to 10. Now we're in the third state. There's 4 top-level statements. There's initialization of k, initialization of n, a for loop, and an output operation. So 4 top-level statements. And we have some repetition here in the for loop. Repetition of substatements. So if you look at the for loop, you'll see that k is not modified. So k is constant in the context of that for loop. In fact, we don't modify k anywhere in here. So if you look at the loop, we're just running we're starting at 0. I starts at 0, and it takes on the values 0, 1, 2, all the way up to 23. When I becomes 23, we don't execute the body of the loop. That means we executed the body of the loop when k was 22, but not 23, 22. But remember, we executed the loop when I was 0, 1, 2, all the way up to 22. That's 23 values, because we started at 0. If we started at 1, we'd have 22 executions of the body of the loop. We started at 0, so we have 23 executions of the loop. And look at what happens in the loop. We add 1 to n. So if you do that 23 times, if you take an n, which starts at 10, and you add 1 to it 23 times, you add 23 once. That's the same as adding 23, right? So we're adding 23 to n. So n becomes 33. So we're confident of that, right? We stop there. We say n is 33. Now, we don't output n. We output n plus 2. So we're going to output 35. All right, that's how to analyze that one. You need to practice those. And remember, if you're not getting this, if you didn't get that problem, you need to create practice problems for yourself. Create a problem on your own. Change it. Make k 17. Make n 100, and change the for loop a little bit, and instead of adding 1, add 3. Play with it and challenge yourself and practice figuring it out. And of course, you need to actually implement the program and run it to verify that your answer that you came up with manually to determine whether your manually computed answer is right or wrong. So that takes time. You got to put time into this. So if you're not getting this now, you still have a chance, because we're going to be doing more of this. This kind of question will appear on the final exam. And of course, the other exams that we're going to do in the lab exercises also rely on your ability to understand this. So I would start practicing this now. If you didn't get this on exam, you got to start practicing now and do what I said. I recommend you do what I said. Create your own mental challenges. Be creative about it and spend some time with it. All right, number 5. When the code in figure 4 runs, what does it output to the console? All right, this one right here. There's one variable I, and I is set to a 5 initially. And then there's 3 statements. There's an initialization of I, a while loop, and an output statement where we print I. So while I is less than or equal to 405, so it's currently true the first time we hit that condition. So we're going to add 200 to I. So I becomes 205. And then we're going to test the loop condition. It's still true. So we add 200 to I. Now it's 405. Is the loop condition true? It is. So we add 200 to I. And check the loop condition. Is the loop condition true? It's false. So we're done the second statement. We are finished the while statement. Now we do the third statement. We print what's stored in I. We're going to print 605. There it is. All right, what about the next one? When the code in figure 5 runs, what does it output to the console? right, this has to do with understanding division, the difference between integer division and floating point division. So I is an integer, j is an integer, and x is a floating point number, a double precision floating point value. That's why we declared a double. That's the shorthand for that term. So x is a floating point value. You can see it's set equal to 1.0, just to emphasize it. I could have gone x equals 1. That would have been okay. It would still be a floating point value set to 1. But I put the 0.0 in there just to emphasize that it's floating point. So I divided by j, those are two integers. That means the compiler interprets the division as integer division. So I divided by j produces a 0. Because normally it would be 0 plus, a half, but the half is discarded. So we print a 0, and then, well, there's an end line there, so it would be like a new, we would do return, and then x now the numerator is a floating point value, so the compiler interprets a division as floating point division. And now we get a half, and so we'll print a half. You could put 0.5, that's all right. You could put 0.5, that's okay. What about 7? When the code in figure 6 runs, what does it output to the console? Well, there's a variable I that's initialized to 4. There's a variable k that's used to control the loop. Okay, sometimes we call that a loop counter. And k doesn't change other than the normal loop process that's used in. So k starts at 0. And it goes up to 299 and runs the loop, body of the loop. But when k hits 300, we're done the for loop. So that means the loop runs exactly 300 times. So what do? We add 3 to I 300 times. We add 300 3s to I. Well, that's 900, right? 300 3s is 900. So we're adding 900 to 9. Sorry, adding 900 to I. I starts at 4, so I becomes 904. That's that's the effect of the for loop. And now the third statement is to print I, so we're going to print 904. All right, number 8, write code that prints 300 random integers that are less than 2,000. A lot of people got confused about this. It has to do with like your reading comprehension. Are you going to print 300 random integers, or are you going to print 2,000 random integers? See, when people were reading the sentence, it was very common. They reversed this. So they made a loop that ran 2,000 times. Well, I don't want 2,000 integers. I want 300 integers. Do you see that? So you got to maybe spend a little more time reading the sentence, making sure, ask yourself questions, and just going back and parsing the sentence again, making sure you're reading it right. Write code that prints 300 integers. 300 integers. We're going to need a loop that runs 300 times. Not 2,000 times. Let's use a standard loop that runs exactly 300 times. There's a standard loop that runs exactly 300 times. It's just like this loop here. Like, it's exactly that one right there. That's it. This loop ran 300 times. You could have just copied that from there. Now I'm using I, you could have used K or N, doesn't matter. All right, so we need to print a random integer. Now this is what I mean by incremental development. You know, I forgot all about what I needed to do 300 times. Just something, right? Let's put that away. I can't keep everything in my head all at once. So we got to do something 300 times. You see how, if you can break the problem down like that. You say, well, so let me write the code that does this something 300 times. And then once I got that down, then I'll stare at and focus in on what it is I need to do 300 times. So we need a random integer that's less than 2,000. A random integer. Well, let's just start with a random integer. There we go. This is a random integer. We call it a rand function. All right. But it's got to be less than 2,000. And we've gone over this trick several times, and you're going to need to know this trick for the rest of the course. You've got to use the Modulo Operator. If we divide by 2,000 and throw away the quotient, throw away the result but keep the remainder. So you can call this a remainder operator. It's the random number divided by 2,000. What remainder do I get? So you're going to get a number that's between 0 and 1,999. We don't want 2,000 because we want a number to be less than 2,000. You see, the key there, and a lot of people got this wrong. They put 2,000 here and 300 there. I don't know why. Why did you do that? I think, but the way to avoid doing that is to try to split the problem a little bit. If you could say, well, look, I know I got to do something repeatedly. Let me just call that a black box. Something. I got to do something. And I'm going to forget about the details. Now, how many times do I need to do this thing? And then go back to the instruction and read it again carefully. I see. I got to do this something 300 times. I need 300 integers. You see how you can debug you could have started the process like this. If you had started, this is good, this is great. If you had started like this, actually, many of you got this, but you stopped with that. If you got this, you came up with this, then you should check your work. You say, all right, I'm printing 2,000 numbers. And then you go back to the problem, read it again. Write code that prints 300 numbers. And you see, if you go back and try to check it, then you're going to say, oh, I got it wrong. I got to print 300 numbers. And then you can catch the boat that way. I got to print 300, not 2,000 numbers. So what's the 2,000 for? Oh, the numbers are less than 2,000. Oh, so that means I got to divide by 2,000 to get a remainder that's less than 2,000. So that would have been an okay process. That would have been fine. I mean, that's how, that would be a natural way of solving the problem. I think you didn't, for those who got this wrong in that way, I would suggest to you that you weren't paranoid enough. You weren't persistent enough. You got to doubt your work. You got to look at it like a scientist. You got to try to, you have to debug it. You have to look for the fault, the failure in your reasoning. You know, when they do software testing, it's an important part of software development. You get these software testers, and you know that you got the developers. It's like one group, and then you got the testers. That's the other group. And the tester goes in, and the developers are terrible at testing their code, right? You can imagine. They want to go home. They want to relax. And so the testers, if they don't do a very good job and they just tell the developers, oh, good job, we ran the program, no problem, let's all go out for lunch now. And but then the product is going to hit the shelves and the customers are going to find the flaws. It'll cause a failure. So when you do the testing, you have to try to break the program. You've got to make an effort, a strong effort, to find the fault. So you have to attack it. So you write down your code. You're like playing the role of the developer, and you get your answer down there. Now you've got to switch hats. Now you're the tester. Now you're the enemy of the developer. You're going to find the fault. All right, so write code that, we did that one. 9, write code that computes the sum of integers 100 through n. Inclusive, that means we include 100 and we include n. Where n is an integer strictly greater than 100. So when I say it like that, n is an integer strictly greater than that. That means just use the n. You don't have to declare it. You don't have to do C and N. You can if you want, if that helps you think the problem through. But I'm saying just assume that N exists, it's strictly greater than 100. Otherwise, if it's less than 100, then the code is a little funny. So write code that computes the sum of integers 100 through N. This is a standard problem. It's kind of a beginner's problem. So you should be pretty comfortable with this. And after this, you should do things like compute the average or all the even numbers that are between the sum of all even numbers between 100 and n, something like that. So we'll get to more of those problems as we go through the course. So what we need to do is take 100, add to it 101, add to 102, and we got to keep going until we hit n. We got to add them all together. So that's n additions. I don't know if is it n additions? That's n, yeah, it is. It's n additions. That's n additions. So we need to repeat something n times. Let's use I for that in a for loop. So there's some structure right there. That's going to give us the ability to repeat that summation operation n times. Or actually, it's n minus 100 times. Oh, see, I got it wrong right from the beginning. This would be very inconvenient. Let me start from there. I should start 100, right? Does that make sense? Yeah. Oh, and also, wait a minute. It's inclusive. I said inclusive here. So let's center equal to n. Yeah. You see, I put out some approximate solution now. Now we're refining it. We're fixing it. We're polishing. All right. There we go. So look, I takes on these values. It takes on 100, then it takes on 101, then it takes on 102, and all the way up to n. N takes on all those values. So for each of those values, we need to add them. We need a storage location that accumulates the sum. So I'm going to declare a variable here, int sum. I'm going to initialize it to 0. And I'll go sum equals sum plus what? I. So there it is. That's the answer right there. We don't need this. Another way to write this, which I think is easier to understand, is whatever sum is, let's add into it I. Let's add I into sum. Whatever's stored in sum, increase its value by I. All right, 10. Describe the Unix command ls. It lists the contents of a folder. There's lots of possible answers. It shows the files and folders within a given folder. It doesn't show the folders within a folder. It shows the folders and the files within a folder. It doesn't only show folders. It mainly shows files. Actually, a folder in Unix is in fact a file. It's a special type of file. A folder is a special type of file at the deeper levels internally. So if you put your answer, it shows a list of files. I accepted that because folders happen to be files. But if you said it shows a list of folders, that's not right because you're missing the files. So there's other variations of that I accepted. What about 11? Show the Unix command to change the current directory to a temp folder within your current directory. You know, maybe that's a little hard to understand. I can understand that. cd temp. Assuming that, and another possible answer, cd, say, the temp directory. Or, you know, different students used it. They said, I think I saw some do this. What I meant to say was that the name of the temp folder is temp, and you just want to cd into that from your current location. And I'll show you what's not correct. This is not correct. That's temp in the working directory, but I don't want you to cd into temp in the working directory. I'm saying that your current directory, which could be, you know, many levels below the working directory, I mean the home directory. This says cd into temp within your home directory. But that's not what I stated. I want it to be in your current working directory. So this is the correct command. So this one will not work. That's your home directory. All right, what about 12? Show the Linux command to delete a file named main.cpp from within the lab1 folder within your current directory. A lot of people got this one wrong. rm is the command to remove a file. Now it's main.cpp, right? I don't know why people did this, but they did this. I don't get it. So many people did that. Anyway, that's not it. So there's a folder in the current directory called lab1. And within that folder is a file named main.cpp. So there's the command right there. Another version, if you wanted to put it like this was also acceptable. Now, some people did this. That's okay. Up here, same with here. You know, that dot is the current directory. Once again, a solution that's not acceptable is this. That's not good because lab1 is not necessarily in your current directory. It's in the home directory, but that may not be your current directory where you are. I didn't say what the current directory was. I didn't say the current directory was the home directory. So that solution wouldn't work. Now, what about 13? Describe the Unix command remove directory, or rmdir. Remove a directory. I'm going to give you a bunch of solutions that were okay for me, right? Remove a folder. Delete a folder. Delete a directory. Those are okay. Oh, here's an even better one. I took those, but here's a better one. Remove an empty directory. That's better, because you can only use the command successfully with an empty directory. This is a very good answer. When I saw that, and many of you did that, it was a very good answer. But I'll show you an answer that's not acceptable. This is a good one. Delete the files in a directory. No, rmdir will not delete any files in a directory. Delete a folder and its files. You know, these are not good. It will refuse to delete files. That's the point there. You need to use that rm command here to delete files. After you've deleted the files in a directory, the directory is empty, then you can remove it. You can only remove an empty directory. I'll take these out. Any questions? All right, so once again, the people that got perfect scores and close to perfect, there was a lot of very good scores. You know, congratulations, keep the ball rolling. For the people that didn't make it there, don't give up hope. You can do it, but you've got to make an adjustment. You've got to start to put more time into it and try some of my suggestions about creating problems for yourself to test your understanding. And if you want more help, you can always talk to me. Talk to the computer science club tutors and Jaron Willis and so on. All right, I'll see you later.